Good morning, friends. In the previous videos, we have learned about repartition method and how the increasing of partition to 28 or decreasing the partition, how the benchmark test was performing. When we increased the number of partitions to 28 from 14 to 28, then there was a lot of shuffling happening and the performance was degraded and it took more time. And when we repartition it back to a lower value, because the data size is very less as compared, so uh, repartitioning to 7, it was a better performance than 14 or 28. In this video, we will learn about Coalesce now, which is a improved method or performance efficient method when we are trying to reduce the number of partitions. So this is what we will test it here. So to save some time, I will just copy this first. I will copy this and paste it here, and then change all this to say Coalesce. Yes, Coalesce, spelling is correct. We'll just use this here. Benchmark test. Just to note that this Coalesce method, I will change it to Coalesce. Okay, and Coalesce. Okay. Okay. So let's revise what we have done. So it's very much similar to because I just copied it from the previous repartition method. So let's revise completely that. First of all, we created a Spark conf object with set master as local star, which means that it would be creating 4 worker threads because I got 4 CPU cores in my laptop. And then we created a data, which is a list of doubles of the size 1 million. And then I created added some random values to it from 100 to 147 something. And then we have got this benchmark test where we are passing this RDD and the operation, whether it can be repartition or it can be coalesce, just to like distinguish between both of these methods. And then we do the benchmark testing by just doing a reduce method on this RDD being passed. Okay, and then we also print that what is the time elapsed and the number of partitions. In the previous test case, we did the same for repartition, and in this unit test case, we will do for coalesce. So coalesce will again do the first of all we'll printing the minimum partitions, which will be coming out as 2 because it's running locally, and the default parallelism would be I think 4 because we have set local start, which is the number of CPU core threads that we have. So it would be 4. After this, we create parallelize. We call parallelize on this data the list of double that we created, but we override because to the number of partitions from whatever default from 2 to 14. So that we can have a better effect of what's going on with the coalesce method. So we increase it from 2 to 14, and then we created our RDD from this data. After that, we called the benchmark test with this RDD with the partition of 14, and we call this as coalesce. This is the default one of 14 partitions. Then we try to increase from 14 to 28. But coalesce, this will not work. It will still, because coalesce can only reduce the number of partitions. It cannot increase. So 14 to 28, it will not work. So this will still be 14. Okay, 14 partitions. It cannot increase it. So if you try to increase it, then it will just disregard that request, and it will still take 14. It will not throw any error or warning. We can check that later in the logs, but yeah, it will not have any effect. It will still be using the original one. After that, we reduce it. This is what it is optimized for. Coalesce will not cause the shuffling of all the data. It will across all the partitions, just like repartition. In repartition, the data is always shuffled across all the partitions. But Coalesce will try to optimize it by just smartly choosing some of the partitions for which the data can be shuffled across. It will not cover all the partitions to be shuffled. So let's run this now and see whether it works or not. So I click on this run button here, and let's see. So it's running now. As we can see that default is 2 and parallelism is 4 because we have got 4 CPU worker threads based on local start. And then it is trying to calculate the sum. That is, we want to see more about the time it takes, right? So first of all, it took like 1.5 seconds for partition of 14. So this is the first one for 14. For the second one, I think 28 will not have any effect. So you can see that it's still number of partitions is 14. So that's why it's still it's not changed when we change it to 28. and then further it's going for 7 when we reduce from 14 to 7, and then it has increased. So let's analyze this. So first of all, we run it with 14 partitions, and then it took around 1.5 seconds with partitions 14, and then we try to increase to 28, which will disregard it, which it will disregard, and it will only take 14 partitions again, and it will it's as mentioned here, it's still 14 and 1048 milliseconds. And after that we reduced it to 7, and then it's 1352, which is slightly better than the first one. This was about Coalesce. Now, if you want to do a comparison between both Coalesce and repartition, I think Coalesce should always be used. As mentioned many times, that Coalesce is much more performance efficient because it's very smartly written that it will not shuffle the data across all the partitions, but only selecting few of the partitions which can have a better performance. So just to look at the whole test case, let me run for all of them. I mean, it will just print for both repartition and Coalesce on the same data, and then it would be better to compare it. So let's run this for complete, and then I will just fast forward the video now. Because I have run both the test cases now for both repartition and Coalesce. Now let's see the test results. Okay, let's make some. Okay. So for Coalesce, as we can see that it has the minimal partitions and default palettes would be same for both Coalesce and repartition, because this is first thing that we did do in our unit test case. After that, for Coalesce, for 14 partitions, it's 1.155 milliseconds, and then when we try to increase it to 28, of course it will not work because we can only decrease the number of partitions. So after decreasing it, it's without any effect, it's still taking 14 because it's already optimized. So that's why it's taking much less time this time. And then when we reduce it to 7, then because there was some shuffling happening, but still it was much more performance efficient. That's why it still slightly took more time, but still it's much better. So the Coalesce performance we can see is that for 786 milliseconds is too less. Now let's go to the repartition. Repartition is again same. So for the first 14, it took 670 milliseconds, which is a very good performance. But after that, once we increased it to 28, because a lot of shuffling was happening, it took maximum time of 1416 milliseconds. And then when we reduced it to 7, of course, again the shuffling data would be happening, and then we can see a very increased performance improvement. When we reduce to 7, it's just 896 milliseconds. So this is what is all about repartition and Coalesce methods. I would suggest that never use repartition for whatever reason if the data is very huge, because it's a very costly operation. It has got some use cases. Once you are creating the RDD first time, and then we want to repartition the whole data in the equal chunks of data across all the partitions after doing some type of initial operations like map or reduce, whatever. In that case, repartition can be helpful. But if you want to reduce the number of partitions, always use Coalesce method. Don't use repartition, because Coalesce, as the API is written to increase the performance, it will not do the shuffling of all the data across all the partitions. So always prefer Coalesce. But in short, you should not use both repartition and Coalesce, because both of them have got a cost, because the shuffling of data happens here. And we should just rely on the default settings of Spark, which is smart enough. And the new versions of Spark are already having very smart how to have the optimized number of partitions based on the data size. And for the HDFS block size is 64 MB, it will automatically choose the best optimal partitions or the parallelism required. So that was all about chapter 12, Spark RDD, repartition and Coalesce. In the next chapter or the next video, we will cover Spark RDD joins. Yeah, joins are very much similar to SQL joins, where we have inner, full outer, whatever. So this is our topic of our next video. So see you all in the next video.